Okay, good afternoon, everyone. Welcome to lecture 4. Having introduced a whole bunch of optimization problems, varieties um, have been also formulated. We also gave a basic introduction to gradients, etc. What we'll do today is discuss some homework exercises which had to do with gradients and Hessians, and then move on to convex sets and convex functions, which are very critical building blocks for continuous optimization. So it's with basically continuous optimization in mind that we talk about convexity, but they also have um, a role to play in discrete optimization problem. Even say submodular minimization, right, can be addressed using convex reformulations. Okay, so for several reasons, it makes sense to understand convexity, and in fact, a lot more reasons. Um, as I'll point out, even for non-convex functions, there are very important regions of convexity, and those often hold the key to solving those problems effectively. So let's do the homework exercises very quickly, understand, if you have any problems. So derive the gradient and Hessian for the following loss functions. Anyone has any thoughts? Hinge loss for SVMs and least squares loss should be easy. Simple two-layer functions, which also have this element of hinge loss here, yi minus max of 0 comma w transpose xi plus b. So you'll find the same element in both places. This max kind of component. What do you do in such cases? And then the soft max. So any questions, any thoughts? Anyone has attempted and faced problems? So if they're not, if there are no questions, then I'll probably move on. I don't want to spend too much time. But in all these cases, what you have to keep in mind is basically the chain rule, right? You'll have to make use of chain rule extensively in all these cases.
Sir, for the last one, softmax function,
Mhm.
here we have exponential of the W transpose A of xi that has label AI, right?
Yeah.
And in the below we have sum over all the labels.
Some over all the labels, correct.
So here the W will have multiple dimensions, like it will be a 2D matrix instead of one.
Right. So there will be actually ideally I should put a WAI transpose. So for every class there could be a separate W. But yes, otherwise you could think of this W as a big matrix indexed
So
into the respective columns.
yeah, so I will find the gradients, but what about Hessians? How will that be? It will also be 2D matrix, or it will go to 3D matrix?
That's a good question. One, yeah, you could actually come up with 3D, that is tensors. You could also think of serializing all the vectors, right? The
Yeah,
entire
like flattening
W
everyone.
matrix,
Yeah.
flattening could do both ways. Very good question. So uh, here W is ideally a matrix. So Hussein can be obtained as a matrix by vectorizing the matrix of weights. Okay. Anything else? Any such observations would be very welcome. What do you do in this case of his hinge loss? You have a max. I have talked about it in the past, but is there a point of non-differentiability, a point where we can't come up with a gradient? And what do you do in such a case? Any thoughts? Yes. So where is a gradient undefined here? The gradient is undefined where this max takes a 0 value, right? Wherever the max becomes 0. So at that point you'll have to think of something beyond gradient, and as we'll develop later on, there's a notion of subgradient. Okay, and I think I gave you an idea, but the point where you have the non-differentiability, right? So let's say your function is like this. Suppose, actually ideally you should make it convex. Okay, so let's say the function is like this. So at all these points, if even this function is convex, um, there are these points where the kings. But what you can do at these points of kings is you can define these cones of all possible perpendiculars. So these give you subgradients. Okay, so these are for convex functions. There exist subgradients at these points of non-differentiability. I'm sorry, I showed you a concave function. Let me just flip this. Okay, I should have shown a concave function. It's true for concave also, but you have something called a super gradient there. Okay, so the same idea here. You'll have this. So these are, it's not just one subgradient, but they are called a subdifferential. Okay, so points of non-differentiability, you have subdifferentials. Okay, these are also other reasons why we are interested in convexity. I kind of develop it very soon. If you didn't have convexity, then you couldn't really talk about, although convexity in some region, you couldn't really talk about points of non-differentiability. What do you do there? Convexity is always going to be important for some of these reasons, many other reasons as I keep developing. Okay, other than that, it's very easy to derive the gradient for this function, but we'll develop subgradients a little later. Any other question? Otherwise, let's move on. I mean, I did this for the regularized logistic regression. You can recall that. I mean, from we basically applied the chain rule here, right? I'm just reproducing from the last class. We said that for this part we had a chain rule, summation, then there's a log, and then I kind of color coded and explain where that log basically goes in the entire derivation process. So we've done this, and you were asked to kind of make sure these derivations hold. These were samples. So let's go back to convexity and motivation. I mean, why is convexity important? Um, every first reason is that every function has convex regions. Even if a
Hello,
function is
sir.
non-convex. Yes, question.
Yes, I have a doubt on the Hessian part of the last regularized. Yeah. The differentiation of sigmoid function is sigma into 1 minus sigma of the function, right? So how do we get this, obtain this xi into xi transpose?
So what is xi transpose? First of all,
The
what
feature
is this?
vector, that is a matrix.
Yeah, it's a matrix, right? So it's a column. Xi is always a column, right?
Right.
By default, and xi transposes is row vector. So this is basically going to be a rank 1 matrix.
Mhm.
and the entries of this would be of the form. What would be the if you take xi transpose, let's say pq. What is the pq, the entry of this? xip
XIP, XIQ.
xiq, right? So it's just product of those two terms. When you take the Hessian with and look at the ipq term, right? So if you look at the pq term here, the Hessian's pq term is nothing but the double derivative of the loss with respect to wp wq. Okay, so if you just try and get these two together, okay, so this, let me put it here. So you try and match these two expressions from double derivative. Go back to the gradient slide, right? We showed this the jth component or pth component here. You'll have minus yi xij exp and so on. Right? So now this xij or xip, if you take the pth component, and now if you do another derivative, what will happen? You look at the expression sitting here. You'll have one more xiq coming out, right? The part in blue here will have an xiq, because when you're taking derivative with respect to wq, after having taken first derivative with respect to wp, again that other term will also come out. So by the same argument we have on the gradient, you'll have xip into xiq for the pth fixed derivative. Is that helpful? That's the intuition.
Right, sir. But how does the yi component vanishes in the Hessian?
So there will be actually a yi square. See, this I is not an index, not indexed
Okay,
by
okay,
p
okay.
or
Yeah,
q.
yeah, yeah, yeah. Right,
It
right,
will be yi
right,
square.
right.
That's a good
Right.
point. Good. I mean,
Thank you, sir.
you should ask such questions. So, okay, this is one, and then the other is, in addition to this, we'll have yi square equal to 1. These two should explain why I get this expression. Any other question? Okay, so these are the two reasons why this holds. At least two reasons. Okay. So let's continue with, unless there are more questions. Every function will end up having convex regions anyways. Okay, that's one. That I've already given hint several times, but these are all the convex regions we are talking about for this function. In fact, these entire regions. This is one convex region, this is another convex region. And many deep learning models exhibit such losses. Okay, you have to remember deep learning models are typically compositions of multiple layers with activation units which are often like sigmoid, right? Or sigmoid like. So compositions of activation units such as sigmoid. Because of that, they exhibit such losses. Or for that practical matter, most will exhibit such losses. So therefore, algorithms, when we look at their convergence, let's say an algorithm starts here or here, right? When we study its convergence, we are really looking at its convergence to some local region in the or minimum in the convex region. So we are talking about this convergence in convex regions of the function, and that's the reason where we get interested. But there are more reasons. I gave you one reason already. Let me recap, right? We already saw this, that for convex functions at points of non-differentiability, you have such subdifferentials or subgradients. That's already a reason we have discussed. So instead of saying convex functions, for convex regions of functions, I can now extrapolate it. So it could be that this function again becomes non-convex in some places, but at least for these regions, I will be talking about. I could talk about subgradients. Please ask me questions, otherwise I'll keep moving on. The domain constraints optimization functions we'll see will also be typically convex sets, so that algorithmic updates are guaranteed to lie within the set. So we'll see how convex sets play a very critical role. You're making this is like a two-dimensional view, or the space of the parameters. The parameter space, let's say, is this way. Now in this space, when I make updates to the function, I want to make sure that I continue lying within the space. Sometimes the space results from constraints. Okay, so my update has gone, let's say, from here to here. How do I guarantee that my updates are within the set? That helps, or that is possible when the set is convex. Okay, so set, this is the second point is about convex sets or convex domains. This is a convex set. Now this becomes very important, especially for algorithms, even in the case of non-convex functions. When you're looking at algorithms within constraints, you need algorithms such as projection algorithms. Right? We'll see Frank-Wolf and there are many other variants of that. Interior point methods, especially important for projection algorithms. Frank-Wolf, interior point, basically Lagrange multipliers based methods. So since that could be a question, I'm just providing the motivation up front. So what we'll do is yes, there was a question, I think. We'll begin with convex
Sir,
sets and then move on quickly to convex functions. Yes.
sir, what is convex set? So, what is difference between the convex
I'll
set
be
and
I'll be defining. I'll be defining. But largely speaking, I'm saying convex sets let you remain within the set. The updates remain within the set, the space of interest. But let's define convex sets. This is just a motivation. Okay. Any other question? Okay, so if there are none, let's move on. So a set C is convex if the line segment between any 2 points lies within the same set. Now, basically we are saying that if you have 2 points X and Y in the set, then you want to make sure that for any lambda which is between 0 and 1, the line segment, the interpolation will lie within the set. Now for this should be true for any 2 points X and Y. This is any two X and Y. So the X and Y can keep changing. I can just translate it, rotate it. It should just hold everywhere. I can scale it. It should still hold. That's the point number one. So you can see here that there exists a set of points X and Y in the set on the right hand side for which the line segment doesn't lie within the set. Okay. The many use this is certainly not convex. The one on the right is not convex. Okay, whereas the one on the left is convex. But there are many other convex sets. In fact, the entire vector space can be thought of as a convex set. How about this? So let me define, let me give you a small exercise. Okay, so here I have this ray, okay, which begins at x and it has any point y here. And the way I'm defining is that for all lambda1 x plus lambda2 y such that lambda1 comma lambda2, that is both are greater than equal to 0. Now, what about this set? Is this convex? Any
Yes,
answer?
this is no,
Is this
sir.
convex?
No, sir.
Why isn't it convex? I'm saying for all x lambda1 lambda2 greater than equal to 0, not just for
So,
lambda1 plus lambda2 which sum up to 1, right? So let's understand the three settings. Okay, this this is my definition. Now the what I've shown here is a special case. This is when lambda1 and lambda2 are both greater than equal to 0. In fact, sorry, that's what I've shown here. So that's exactly the array here. But I can show you another, I can give you other combinations of lambda1. But let's say I look at a specific case. This is, let me just highlight this in to itself. But a specific case of this would be when I have x here, y here, the same x and y. In fact, let me just copy it. I'm taking the same x and y, and I'm trimming off this part. Okay, so this special case is what? Lambda1, lambda2 are both greater than equal to 0. But additionally, what do I have? That both of them are going to sum to 1. So I put an additional constraint to create a line segment. If I don't have this constraint, this is how it would look like: array. Array. Now, is ray a convex set? Line segment is a convex set. So any 2 points you take within this line segment, you interpolate them, you'll get a new convex set. I mean, you get a new line segment which lies within the set. Is ray a
Sir,
convex set?
yes,
so
sir.
that thing, lambda 1 x plus lambda 2 y, where both are non-negative, that represents a triangle. I mean, an infinitely long triangle, basically 0 to x, I mean, origin to x, origin to y, and the triangle between them going off to infinity.
Yeah, cone. Actually, in this case, I've shown them in. This is when x and y are in, say, good point. This is when x and y are just one dimension. Okay. But what you're talking about is another case where x and y are, say, in 2 dimension, right? Then it look like a cone,
Yeah.
right?
So it
So is
will be
cone a convex set?
convex. Yes, sir.
Yeah.
In
So
both 1D and 2D.
in 1D and 2D, it's always convex. This is yeah, this is an example in 1D, but in 2D also, you what we have done is we have just removed that. We are saying for all values of lambda1 and lambda2 greater than or equal to 0. So we have removed the lambda1 plus lambda2 equals 1 constraint. So this is a convex set. Okay, this is okay. This is exactly called a convex cone. Okay, so I'm saying if this is in the set C for all x and y in the set C such that lambda1 plus lambda2 is greater than or equal to 0, such a C called a convex cone and is a convex set. Okay, so there are many special cases of convex sets. I mean, what you saw here, for example, is a ray. The is a right. This is a ray, and ray is also a convex set. So lots of convex set, linear sets, affine sets. So for example, let me give you one final example. Again, I have my detailed class on convexity elaborates on all these special cases, but I'm just trying to understand, get your horizon right. So another use case, another example is, say lambda 1 x plus lambda 2 y for all lambda 1. So now what I'm doing is I'm dropping that lambda 1 and lambda 2 are greater than or equal to 0 constraint, and all I'm saying is lambda 1 plus lambda 2 equals 1. Okay. Is this a convex set? The answer should be yes. All I have done is drop the positivity constraint. Okay. So if you take any x, y, and c, if this is in C, I mean, we're saying if this part is in C for all such combinations, then we call the C an affine set, and it's a convex set. Okay, so there are lots of special cases of convex sets you can get by relaxing the lambda. So here we have relaxed the lambda positivity. Here we have relaxed the in the case of a convex cone, we have relaxed the summation to 1. Okay, so it's just interesting to know the difference. Okay, any questions? As we'll move on. Okay, so all these are examples. But there are some interesting properties of convex sets. Intersections of convex sets are convex. Okay, so if this is easy to prove. Okay, I'm not going to do all these proofs, but I mean, what you want to really prove here is that if X is in C1 intersection C2 intersection CK, right, and Y is in C1 intersection C2 intersection CK, then you'll have to prove that the union of the two, sorry, the intersection of the two would contain all those points for which both the constraints are satisfied. Okay, this is what you'll do to prove that lambda xi plus 1 minus lambda x1 plus 1 minus lambda 2 x2 is an intersection. Use that this lambda x1 plus 1 minus lambda 2 x2 lambda x2 is in both C1 and C2 and C3 and CK. Okay, simple idea. Now, is the union of convex sets convex? So I'll give you a
No, sir.
they're not, right?
No, sir.
I don't have to even give you example. Why would you say it's not convex?
Like geometrically, like even if you have that hexagon and another hexagon which is like even if it is disjoint, then
Okay, so the unions they may be disjoint. In fact, the union
yes, sir.
could be even disconnected, right? Exactly,
Yes,
you said
yes,
disjoint, they could actually be disconnected. So how
disconnected.
can there be convexity?
Yes, sir.
Yeah, I mean, it's easy to you can just prove by contradiction, right? How do you prove by contradiction? Here's a simple example. You just take set and then prove that this is not convex. Projections are convex. That's very important. And as I said, that's one of the motivations for constraint optimization, right? We said algorithmic updates are guaranteed to lie within the set. So sometimes you are required to project with respect to constraints. And projections onto convex sets are unique. Okay, let me try and illustrate this with a simple example. Let's say you have this case, right? What you see here are a set C, this is in red. You have a point X, which is in R3. Now imagine that this point R3 was obtained using some update rule, right? Somehow this point was obtained, this X. What you're trying to find is a point Y in the C, as highlighted here, a point Y in C such that according to some norm distance, Y is closest to X, or Y is the point in C closest to X. This Z is basically the Z axis. I'll just put it here. Okay, so now it turns out that if the set C is convex, then the projection is unique and often efficient to compute. But let's take an example where the set C is not necessarily convex, or S is not convex. How will it look like? Let's see an example here. If the set S is not convex, the projection of X onto S need not be unique. You see this here? So it's not even unique. This X here, when you try and project, find the closest point in the set S, you don't find one closest point. This is also closest. I mean, the 2 points that seem to be closest. That's largely because the set was not convex. But now if you were to extrapolate this S, right, to contain, let's say, a larger region, which also makes it convex, let's say extrapolate, then you'll find that there'll be a unique projection. But I'll not put that here. So hopefully this is clear. Any questions? So a convexity makes a lot of sense because, again, because projections become efficient to compute, they are unique and so on. Some more examples I'm giving here. And for example, if you have norm ball, so you have a norm and you want all X is that norm of X is less than equal to K. That's called a norm ball for any valid norm. So this norm ball happens to be a convex set. Okay, so let me give it a name here. It's called the norm ball. Another example of convex set is the hyperplane, or actually half space. All the points that lie, say, below K in terms of the dot product with a fixed W. So these give you something called a half space. Okay, we'll see a little bit more on that the subsequent slide, at least the norm ball. Now a very interesting example is that of a sublevel set. Okay, so this is called a sublevel set, third one. Again, it turns out that that is also a convex set. Now I'm going to leave all these proofs homeworks for you, so you can try and prove them as homework. Some of them I'll try and provide. So sorry. But the intuition is going to be the same. The same intuition is going to hold everywhere, which is I want to somehow show that a point that belongs to 2 points that belong to the set, their convex combination will always lie within the set. In the case of intersection, I had to show that 2 points belong to each set, then the convex combination will belong to each set, for example. So I have to follow the same logic everywhere. The exact inequality that comes to rescue could be different. Okay. But norm ball, while we say it's a norm ball, it's not. I mean, don't just go by geometry or geometrical intuition, right? Norm ball, yes, it's based on a norm, but it doesn't necessarily look like a ball always. If if for example you're using Euclidean norm, then it becomes like a real ball. Otherwise, you could have norm balls which are of kite shaped, and that is when you, for example, use the L1 norm. Okay, so this is a norm ball. So let me show the norm ball here. Okay, so this is a norm ball under the L1 norm. Any questions? So this basically saying that L1 one norm of x is less than equal to, say, or k, some value of fixed value of k. Questions? Okay. If there are no, let's look at more examples. You can actually create convex sets around any functions using the notion of a convex hull. So convex combination of k points, if you take, that's called the convex conv, right? If you take all such convex combinations of all points in a set S, then you get the convex hull. So what you see here, the ones in black, the black points is S, and what you have shown in gray here is the convex hull of S. Likewise here, the part in gray is the entire gray is the convex hull of S. So one question I have is this guaranteed to be convex always? Anyone wants to attempt? Always going to be convex? Yes.
So I think yes.
So you're saying that convexity of the convex hull is always guaranteed. Is that what you're saying?
Yes, sir.
What about the convexity of S? Does S need to be convex?
No, sir. S need not be convex,
S need
like
not
on
be
the right
convex, right?
side.
In fact, that's very obvious here. In these cases, you find a whole bunch of points whose line segments joining those points is not going to lie. So if you take any 2 points here, the it's not that all the points on the line segment lie within the S. In fact, S only consisted of these finite set of points. Likewise here, if I take this point and say this point or any other point, this point, then the line segment joining these two did not lie in S. It lied in convex hull of S. That's another point altogether. Okay. So answer, yeah, you're right. The answer to this, let me just use a different color. The answer is indeed no. Okay. For the reason we have just now cited. So convex hull is a way of recovering convex sets from non-convex sets. In fact, most convex sets you could think of convex hulls of them as convex hulls of certain set of points, right? So I mean, in retrospect, you could think of all the points along the boundary here, and the convex hull of those points in the boundary basically give you the convex hull. So any convex set be thought of as a convex hull of all the points, and now we're saying they are canonical points, like representative points. Okay, lying on its boundary. Now the notion of boundary has to be defined a little carefully. Again, I have a very detailed previous year's lectures where I on convex optimization where I define formally notion of a topology, a boundary, and so on. But I think for purposes of this course, boundary can be understood very intuitively. Okay, let's move on. Convexity of S is always guaranteed. It's always convex. Let's look at uh, Euclidean balls and norm balls. We'll start with Euclidean balls. So the Euclidean ball is a convex set. This is all very obvious to us when we discussed, right? I mean, a special case of a norm ball. Ellipsoid is also an interesting special case of a norm ball. It's defined in terms of this important expression x such that x minus x c transpose p inverse x minus xc is less than equal to 1. And what is this p inverse doing here? This p inverse is basically a positive semi-definite matrix, but geometrically we can understand this to be inducing both scale transformation and rotation, right? It's doing two things. It's a p inverse is inducing the rotation and scaling of the points within a Euclidean ball. E and its inverse induces rotation and scaling of points within a Euclidean ball. In fact, there are also well-known statistical distances between points which are inspired by this kind of P inverse. For example, you may have this to be the covariance matrix. When P is some covariance matrix, this turns out to be the so-called Mahalanobis distance. So this distance is called. So what distance am I talking about? This x minus xc transpose P inverse x minus xc. I might have got the spelling wrong, but yeah, more or less correct. Okay, and I'm really talking about this expression out here, which I'm going to highlight in yellow. This expression is called the Mahalanobis distance. There are also other representations xc plus au such that u two norm of u is less than equal to 1. Okay. So you can show again this comes from lots of matrix equivalences. Please move it here. Okay, so this representation you can get right, by transforming transforming P into A. Again, I'll leave this as a homework problem for you. So homework, figure out what is the transformation. Okay, any questions? Let's move on then. Norm balls are a generalization of the Euclidean and the ellipsoidal ball, which you saw on the previous slide. You can actually show that this also corresponds to a norm, this kind of distance. And what is that generalization? The generalization is just any norm. Very central to a norm is the triangle inequality, and actually a lot of it is based, many proofs follow from the triangle inequality. Okay, so what's the triangle inequality? If you have P norm of P plus Q, then is less than equal to norm of P plus norm of Q. And this is sufficient. This is a very important step to help you prove that these norm balls are convex sets. So if the question is why is it a convex set? Well, it's by this triangle inequality. Okay, how would you do that? It's not very difficult. I'm just would anyone like to suggest how this can be proved? What would you do? Let's say for any x1, x2 in the norm ball, let's just call this B. So what will you do for any to x1, x2 in B? You look at this distance, right? The distance x minus xc. Now you'll have to do that for the convex combination. So let's say for these two points, you consider lambda x1 plus 1 minus lambda x2 whole thing minus xc. Okay, for this arbitrary p, I don't want to do square and expansion because I don't know the right value of p. I mean, it's for any norm ball p. But what I can do, these are important tricks. What we will do is we'll expand this. We'll say is this lambda x1 and plus. Now I'm going to use this lambda x1 plus 1 minus lambda x2, but I'm going to expand this xc part minus xc minus 1 minus lambda xc. Okay, so lambda plus 1 minus lambda is 1, and I'm just using this p norm. And then if I further rearrange, what I'll do is I'll bring these terms together. So I'll for example bring these terms together and the other two terms together, lambda x1 and lambda xc. I'll bring them together. It's still an equality. So I'll have lambda x1 minus xc plus 1 minus lambda x2 minus xc. Okay, so after this, I'll just use my triangle inequality. Okay, so I'll just make use of this fact that I could go ahead and distribute this. I'll just use, let me just do some color marking. I'll use P in place of lambda x1 minus xc, right? That will get me P all through. And for the other part, I'll just use Q 1 minus lambda x2 minus xc. Okay, I hope the rest is clear. So when you now do this expansion, you'll get lambda times inequality lambda times x1 minus xc plus 1 minus lambda x2 minus xc. You know that each of them is less than equal to r. They both belong to the ball. So it'll be less than equal to, okay, if you want, I'll write it lambda norm of x1 minus xc plus 1 minus lambda x2 minus xc, right, which are less than equal to lambda r plus 1 minus lambda r, which equals r. Okay, so the proof is otherwise, largely going to follow this most of the times. Okay, let's proceed. So there's special case ellipsoid basically we're using a P. So we're going to know, we're going to very soon see norms that matrices induce on vectors, norms that vectors induce on matrices. Somehow we have to give up this mental block, where we see matrices and vectors very differently, right? This question came up, I mean, or an important comment came up early today, right? Even when logistic regression, your multiple classes, just think of unrolling the weights of the weights W of the logistic model, and you get a long vector or its equivalent matrix representation. So a special case basically is this. So you have a matrix induced vector norm, but we can also have vector induced matrix norms. Okay, but we'll look at that later on, and it'll come up very soon. We also have vector induced matrix norm. Okay. Yeah. So these are all special cases. If you have questions, please ask. Otherwise, we'll move on to the next, just convex function. So all this gives you ways of defining the domain on which a function is defined. And as I said, convexity is important for sets so that projections lie within the same set. But we are going to see more of convexity of sets as we look at convexity of functions. In fact, a traditional course on convex optimization, we have a dual view of sets and functions. In a conventional course on convex optimization, there's a dual view involving sets and functions. Okay, so while we see sets and functions so differently, especially when it comes to convexity, there are some very interesting dual views that hold. But we'll see that a little bit more maybe through the course as we proceed. So let's move on to convex functions. So convex functions require the set to be convex upfront. That has been declared here, that a function f is convex, first of all, if the domain f is convex set. You really can't talk about a convex function on a non-convex set, because as you'll see, you are basically ensuring that all convex combinations of the function should be such that the function is defined there. Okay, so this is the convex combination of points in the domain. Secondly, what we require is that the function at the convex combination of 2 points is a lower bound to the convex combination of the function values. So this is the interesting new twist to the story. Okay, so we are saying that the function at the convex combination, plain words, this must be less than equal to the convex combination of the function. Of the function values, more to be more specific. Okay, so I hope this is okay, and you can see it here. So the function is shaped downwards to show that the function value at the convex combination is actually less than the convex combination of the function values, that is this part. Use a different color, that this part. And another intuitive explanation is that, like, basically line segment between x and fx and y and fi lies above the graph. This is the graph. When we say graph of f, we basically mean the part in green here. Sorry, got muted. Any questions on this? I was just trying to ask the questions. There are lots of variants. So like we have convex functions, we have something called strictly convex functions. And all that is required is that the point lies, the convex combinations lie strictly above the graph. Okay. So everything we have said above, including the inequality, just becomes strict inequalities. One important point is we don't consider lambdas which are 0 or 1 because those will coincide with the x or the y's respectively. So we'll only look at lambda strictly between 0 and 1. That's true for helping generalize. Okay, so what is strict convexity doing? It's just saying that there is a insisting on a gap, right? Insists on the gap, and the gap is basically between the graph of the function okay, so it's, yeah, between the graph is really between the gap of the thing went wrong. Here, this is the graph. Now the graph, you should understand this. This gap is measured along the y-axis, the function axis. Okay, so you can't take a perpendicular to the line segment itself. Now you have an additional notion of strongly convex functions, which is a special case. All these are special case. Strict and strong convexity are special cases of convexity. The difference is that strict convexity talked about a non-zero gap, whereas strong convexity is talking about a functional gap. So it's talking about a function-based gap. Both are special cases of convex functions. Okay, so what is a functional gap here? Well, it is basically okay, so this function-based gap here is this mu by 2 into norm x square. This mu is called the strong convexity parameter. I must tell you that this is just one form of gap, one form of functional gap. There are also other functional gaps possible. For example, there's a notion of a Bregman divergence, which looks at some other kind of there could be entropic gap, right? So there are other function based gaps also possible. Okay, there are several other algorithms which also make use of these gaps, but let's use this quadratic function as a canonical example. As I pointed out, these are special cases, so which would mean that strong convexity, and in fact for that matter even strict convexity imply convexity, but strong convexity actually implies strict convexity. So this particular function norm x square, right, it becomes 0 only when x is 0. So therefore its strict positivity implies that strong convexity implies strict convexity. But it doesn't mean that strong convexity makes a function differentiable. Can you give an example of a strongly convex function which may not be differentiable? Anyone? You may think that just because I'm adding a mu by 2 norm x square, I'm getting differentiability. Mu by 2 norm x square may be differentiable. Would anyone like to give an example? In fact, the example is very much there in our discussion. We have already discussed such an example.
the hinge itself.
Right, right. If f is hinge, right? If f is hinge, add this mu by 2 norm x square, and rather, yeah, if you add this mu by 2 norm x square to a hinge loss, you'd get strong convexity, but it's not differentiable. Right, plus norm x square. Though f plus norm x square is convex, that's not a problem. It remains convex. In fact, it's not just convex. Sorry, it's strongly convex. It is strongly convex. So that's an important point. Any questions? Okay, let's continue. So if f is strongly convex and g is convex, but not necessarily strongly convex, then f plus g is also strongly convex. I mean, one example we gave is just norm x square, L2 norm of x square. Right? So L2 norm of x square is a canonical example of a strongly convex function. Okay. How do you? I mean, what basically will this mean? Right. So you'll basically use the inequality, very well known inequality for convex functions, but you have to slap on that the mu by 2 part. So I'm going to some of this can be proved. You try and prove this. Okay, so there's lots of inequalities you have to deal with. Okay, so here are examples of convex functions. Linear functions, the simplest example, A transpose X. Affine functions, you can easily show that they are also convex, and that's again by definition. So many of these just follow from definitions. So by definition, you can just take 2 points x1, x2, show that the affine combination of those 2 points is less than equal to affine combination of the convex combination of those affine transformation of the convex combination of those 2 points is less than equal to the convex combination of the affine transformations of those individual points. Okay, so it's very simple. So you'll have to just say that A transpose times theta x1 plus 1 minus theta x2 is less than equal to theta times A transpose x1. Okay, now you'll have to take the B as well. So this entire thing plus 1 minus theta into A transpose x2 plus B. Okay, so this looks simple. This is just because the right hand side now turns out to be A transpose. You take the theta inside, theta x1 plus 1 minus theta x2 plus B. So you'll have 1 minus theta B plus theta B, which would just become B, which is the same as the left hand side. So we don't have a problem here at all. This is the same expression. Okay, but now you can do this for exponential functions as well. How would you prove that? Well, you have to do the same thing, right? I mean, whatever I applied here, you have to do the same thing here. exp of right. So now you'll have to take this alpha of the convex combination, alpha theta x1 plus 1 minus theta x2. You'll have to prove that this is less than equal to theta times exp of alpha x1 plus 1 minus theta of exp of alpha x2. So how do you prove this? Anyone? So it turns out that there are some associated properties we can make use of, right? So exp is involved alpha x. Alpha is a linear transformation, but somewhere you have to prove that exp is convex. You can plot it, of course. The plot does look convex. Sorry, it does look convex. Um, in fact, every norm is convex. Every norm as a function is convex. Um, some of these you can prove by first principles. Okay, so if the fact that every norm is convex can be proved by first principles. And you can recall uh, proof of convexity of norm ball, right? It was very straightforward. So the same idea will actually hold here. But for exp, you'll have to do a little bit more work. Okay, we will we will derive other equivalent conditions for convexity. The first order or derivative base, and you've done it in your calculus course, right? The fact that first and second order, so increasing derivative, or instead of saying increasing derivative, you can say positive second derivative. But then when we talk about general functions of multiple arguments, you can't just talk about derivatives, you have to talk about Hessian. And Hessian needs to be something called positive definite or positive semi-definite. Okay, so but this part I would really leave it to you as homework. The fact that every norm is convex, I'll leave this as a homework problem. You should really try that because we have done this already, so you shouldn't not require any further effort. Any questions? Any questions at this point? Please do ask if you have. Okay, so I'll leave it as homework problem. Okay. Further, so yeah, every norm is convex. You can prove. I've given the hint here by triangle inequality and homogeneity of norm. Okay, so you can basically use the same idea. This is, as I said, this is going to be a homework problem. Let's move on. Other properties of convex functions. So non-negative weighted sum. If alpha is greater than equal to 0, alpha i's are all greater than equal to 0, sorry, then sum of fi's, alpha I fi's, where fi's are each convex, is also convex. Again, the proof should be very simple. Basically from first principles. Another very simple statement is that composition with a affine function f of ax plus b is convex if f is convex. So for example, if you know that minus of log is convex, okay, minus of log, again we'll show that it's convex through some additional properties, but for the timing it suffices to visualize, right? So it basically is like this. So it's minus of log x is convex. Sorry, it's not looking very convex. Yeah, hope this helps. Now, if you take minus of log of an affine transformation bi minus ai transpose x, then that turns out to be convex. And if you sum it across all values, then I mean sum this across multiple ai bi indices, then that turns out to be again convex. That's a use of non-negative weighted sum along with composition with affine functions. Okay, likewise you can take the norm of an affine function, norm of ax plus b, that's also convex. A simple example of this is what we have discussed. The ellipsoid is an example. We show that the ellipsoid was obtained as an affine transformation of the Euclidean function, right? So affine transformations of Euclidean balls. Okay, so instead of saying this can also be used to show this is related to. So yeah, you can hopefully start seeing corrections between what we have discussed for sets and how they generalize to functions. Now some other interesting properties. Now we are really getting into calculus. This is all really what we call as calculus of convex functions. And we'll do likewise calculus of gradients also later on. So this amount to calculus of convex functions. Now what is this composition saying? It's saying that fx, if it's defined as h of g of x, under certain conditions on h and g, you basically get convexity. There are two possible conditions, and let's start with the first one. So if g is convex, h is convex and non-decreasing. That's the case number one. Okay, let me just show this one at a time. So g is convex and h is convex and non-decreasing. So h need not be only, I mean, h cannot be rather non-increasing. What does that mean? So h cannot have this shape. H can be, for example, an exponential function exp. This could be its shape, right? So under this condition, or there is another set of possible complementary conditions. G is concave. H is convex and non-increasing. H should be again convex, but non-increasing, and that typical example for us is the minus of log x, okay, which we saw on the previous slide. So H is convex, but it's like this. So under these two conditions, it's non-increasing and convex. H and G is concave, or G is convex and H is convex and non-decreasing like exp. Then the composition F can be shown to be convex. Right? I mean, some cases, if your functions are differentiable, you can go back to first order or second order conditions. We have not yet proved them, but no, we can assume that at least in the one dimensional case, we all know the double derivative being non-negative is a kind of condition for convexity, but necessary sufficiency will come too soon. Okay, but that could be a proof idea. And here you see fx equals exp. I gave you that example already, convex and non-decreasing, that example. If f is convex, this always holds. Or 1 upon gx is convex if G is concave. Now, how would you prove this? Can you, of what is this a special case? So the first one I can think of it as a special case of A, right? This is special case of A. What about the second one? 1 upon Gx is convex if G is concave. How would you prove that? So G is concave. How would it? What condition you see here? Well, G is concave is the second one, but H is convex and non-increasing. So is 1 upon X convex and non-increasing? Like to hear from you. What's the function? Exp I said is an example of a convex non-decreasing function. How you prove the second one? Is the second one following from B? I would like interaction, please.
If G takes values, only positive values, then it is a case of the second.
Okay. So it's important that G only takes positive values. Okay, so then let's highlight that part here. That has not been stated anywhere explicitly, but we seem to be assuming that. Okay, so so 1 upon X is convex and non-increasing for all X which are greater than 0. That's what you're trying to say, right? So now if you have, so I mean, you could think of the shape similar to log. Obviously, it's not really like log. So X extends to 0, you become infinity, and then as extends to infinity, it becomes 0. So it's like this. And therefore, if G is concave, and good point here, which has been missed out, which is important, is that G should be non-negative. Now, if G is negative, then what happens? Will this not hold? Just put positive. So if G can turn out to be negative, will this not hold? Yes. So homework. What if G is rather, G is allowed to be negative? Okay. Yeah, think about it. Okay. Any questions? So far we have talked about convex functions requiring, the domain to be a convex set, and we have special case of convex set as a strict convex function. Sorry, special case of convex functions as strict convex functions. We can also have strongly convex functions, right? And here's an important statement I've made here with respect to strong convexity. So if a function is strongly convex for all x1, x2 in domain and theta, if 0 less than theta less than 1 for all of these values, we'll have this condition. So I didn't so far explicitly give the definition. I defined in terms of convexity. I said that f is strongly convex if there exists a mu such that the function g is convex. But it turns out it's the same as saying the following. You can, instead of saying this being convex, you can say that f itself must satisfy this condition, all I've done is I've added this quadratic component towards the end. Okay. So this is that quadratic gap. So we are saying that if f is strongly convex, then even if you remove that quadratic gap, you'll still have convexity. Okay. So you can either add that quadratic gap to a convex function to make it strongly convex. That's the summary, right? Or you can remove that quadratic gap from a strongly convex function to get convexity. Or you can add the quadratic gap to a convex function to make it strongly convex, or you can remove that gap. And now I'm just saying quadratic gap, but you could change it to some other gap for other notions of strong convexity, right? So the typical notion of strong convexity requires this quadratic function. You can remove this from a strongly convex function to make it convex only. Okay, so so far so good, right? And we also seen, how every norm is a convex function. We left that as homework, but let's now move to more complex. So I've seen shown how composition with um, scalar functions gives you convexity, but you can do the same thing with vector functions. Okay, so what uh, is happening here is we saying that f is obtained by applying h to a vector of arguments where each argument can be subject to certain transformations. So exactly what I had described earlier. Now I'm going to do this. Okay, so let me show you this. So GIs are again convex. Each GI can be, that's case number one. And now I'm bringing a slightly different notion of uh, non-decreasing. It's non-decreasing in each argument. It's just convex and non-decreasing in each argument. And what that means is, well, it could be something like exp, but it has to be exp of, say, let's say a product. You could have an exp of product of multiple terms. So can we think of, say, instead of exp of x, I'll now think of exp of x1, okay, into x2 into xk. Okay, so that could be my exp. Now I'm applying exp to say g of g1x and g2x and gkx. Here the x to which g is applied is an Rn. So, okay, so let me not use x, let me use actually different. So as to avoid confusion, let me use this y here. So what we have done is x is an Rn. It has taken us to some, say, y. I can use y or I can use g here. So exp of y1 into y2 into yk. So this is the case number one. Or like before, I could have again gi as concave. Again, I go back to the previous depiction. Gi could be concave. But in this case, I would like h to be non-increasing each argument and convex again. So again, I could look at that minus log thing, but now I have to be a little careful. Can I just do a minus of log of summation? Let's think about it. I'd like you to intervene here. So let's take this example of h being convex. I want your help. Can I now just take h to be, say, minus of log of I'll use y1 into y2 into yk, minus of log of the product, which is basically minus of the or summation of the minus of the logs. Is this a good example of H convex and non-increasing in each argument? Or would you like a slightly different function? From you. Am I audible? I've given some examples here as well. In fact, I've taken log of a GIX summed over all I. Okay, but you could think of this summation of logs as log of the product, given this example here. But of course, now I've changed the there's no negative sign here. So if we are talking about its concavity, it's related to what we are seeing here. But is this a right example? Minus of log of y1, y2, yk, product of these. Is this convex function non-increasing in each argument? Would you agree with me? Yes or no? Could you like to chat and give your vote? Put your thumbs up, whatever, or thumbs down if you don't agree. Your participation is vital here. Or if you think there's another function we should be considering as an example of convex and non-increasing in each argument, please do share. Okay, so I'm not hearing any positive or negative comments. I'll assume this is fine. Okay, so based on this, you can now prove certain allied results. So these results, I'm going to leave them as homework for you. Okay, so please try and prove these as homework. I've given enough hints already in the class. Fx is summation over I of log of Gix is concave if Gi is concave and positive. Okay, so positivity I've explicitly stated here. That's important here. Log of the summation of exp, log sum x. It's also called log sum x, which is very commonplace in graphical models, in use of basically logistic laws in complex models. This turns out to be convex if GIs are convex. Okay, so please attempt these two as homework. We'll begin the class at this point next time. Any last questions or comments?
So the log function is concave, right? Like
Yes.
log in general. So the negative of a concave is it convex?
Good question. Yes, negative of concave is convex. We didn't state that explicitly. Okay, so in fact, we didn't even formally define concave functions, since I don't want to get overly lost in convexity. But negative of in one way of defining one definition of concavity is that the negative is convex. All the inequalities get flipped. Okay. So this we are hinging on this definition. Thanks for bringing this out. Any other question or comment? Okay. If there are none, please do attempt the homework. We'll be very soon releasing assignment 1, but your solving these homeworks will really get you good momentum in solving the assignment. It's important that we are giving enough chance for discussing these homework problems. So please do spend some time on those. Thanks again. Thanks. See you on Thursday.